All right, so chapter 3, section 2 is going to be all about polynomial functions of higher degree. All right, so we've done quadratics in section 3.1, but in this section we are going to do any kind of polynomial, right? So if you remember, a polynomial function is just anything that has a positive whole number exponent, right? So x to the fourth, x to the third, right? If I had negative 5x to the sixth plus 3x squared, right? That is a polynomial function, right? So something like the square root of x, 1 over 3x squared, right? These are not polynomial functions. We need positive whole number exponents in the numerator, right? So anything like this. Now we'll begin the discussion of polynomial functions with end behavior. But before I do that, I'm just going to quickly go over some things that you might need to know. So the degree is going to be the highest exponent. Just in case you forget, right? I know some of these words get lost sometimes, but so the degree is going to be your highest exponent. And we also need to know the leading coefficient, right? And this is going to be the coefficient of the highest exponent, or of the variable with the highest exponent. Right? So for example, if I give you something like negative 5x to the third plus 2x, right? Something like this would have a degree of 3, right? So the degree is the highest exponent. Here between these two variables, the highest exponent is a 3. And the leading coefficient is going to be this negative 5, right? Because that's the number that's in front of our variable with the highest exponent. All right. And now this is going to help us determine the end behavior, right? So an odd degree polynomial has opposite behavior at each end, right? So basically what this means, so in general, when we talk about an end behavior, right, whatever polynomial function that you have, so we know that a quadratic is going to look something like that, right? We've worked with that plenty of times. We know a cubic function is going to look something like that, right? We've seen that before. A line, just a regular old line, looks something like that. Now the end behavior is just going to be the direction that our function tends to as you go to the right or to the left, right? So this quadratic function, you see that the arrows are both pointing up as you go to the right and the left, right? Our cubic function, you see that one's going down and one's going up, right? These are end behaviors, right? So there's a line, you see one's going down, one's going up. Any odd degree polynomial, if a is positive, now a, you can also think of that as the leading coefficient, right? The leading coefficient, right? But any polynomial in standard form is going to have a as the leading coefficient, right? So if you remember, your quadratic in standard form is ax squared plus bx plus c, right? That a is your leading coefficient, all right? And that's the case for any polynomial. If we say a, right, we mean the leading coefficient. So if the leading coefficient is positive, then this just means that our graph is going to fall as you go to the left. So it's going to go down, and it's going to rise, right, or go up as you go to the right. All right, so for example, a cubic function, right, an x cubed. We know that that is going to go down in this direction, right, and the rest of it's going to look something like that. It's going to look like this little snake shape, right, with this end going down and this end going up, right? So as you go to the left, you see that we're going down. As you go to the right, we're going up. And similarly, if the leading coefficient, a, is negative, then it's going to have the opposite pattern, right? So you're going to go up as you go to the left, and you're going to go down as you go to the right. Right? Now with any even degree polynomials, right? For example, a quadratic, so an x squared, it's going to look something like that. And notice that both ends, as you go to the left and right, both ends are going to go up, right? So something like that. And if a is negative, your leading coefficient, both ends are going to go down. All right. And I like to remember all of the, like, there's really only 4 cases with end behavior, right? And I summarize it in a table, right? So one side of it is going to be your degree, and then the other side is going to be your leading coefficients, right? The sign of it, right? So the sign. All right, so I make a little table. All right, so we only have 2 options for the sign. Either it's positive or negative. And we have 2 options for the degree. It's either odd or even. So odd positive, we said that it goes down as you go to the left and up as we go to the right. Odd negative is going to go up as you go to the left and down as you go to the right. Even positive, they both go in the same direction, up. Even negative, they go in the same direction, down. All right, so something like that. And if you want to describe it using words, you can say it falls as you go to the left, rises as you go to the right, or goes down, left, up, right. All right, for example, I'm looking at this one right here. But, I mean, the arrows give us enough information, right? This is really just going to help us graph these, right, when we go to graph in a couple slides. All right, so speaking of graphing, right, more information that's going to help us is our zeros and our multiplicity. Right, so our zeros are just the values of x that we get when we set the function equal to 0. Right, another name for these are going to be roots, solutions, x-intercepts. Right, these all mean the same thing. Right, these get us our zeros, whatever we get when we set our function equal to 0. So for example, if I give you a quadratic function, right, x squared plus 4x plus 4, right, if that's my function, you want to set that equal to 0, and you want to solve it, right? And we had a whole chapter, a whole section on solving quadratic equations, right? So this shouldn't be anything new, right? So we want to start by finding numbers that multiply to 4 and add to positive 4 in the middle. And that is going to get us an x plus 2 and another x plus 2. All right, so we get x equals negative 2 and x equals negative 2. Right, we get the same solution twice. So this just means on our graph, right? So I'm just going to do a rough sketch, right? This isn't absolutely necessary for you to write down at the moment, right? We're going to do some examples, but it might help you follow along, right? So at negative 2, we know that we're going to touch our x-axis somewhere right there, right? And because it shows up twice, right? I had briefly mentioned this when I taught this lesson, that if you get a repeated solution, that's called the multiplicity. And I had said that it was going to be useful later on, right? So we've reached that point, right? So here's where multiplicity is actually useful to us. The multiplicity of a solution, of a root, is the number of times that it occurs, right? So for example, in this problem right here, we see that we got a solution of x equals negative 2 twice, right? That just means this solution has a multiplicity of 2, right? Because it shows up twice. And this is useful when graphing because if it occurs an even amount of times, then it just bounces it, right? So even, it touches and bounces in the other direction, right? So it just hits it and turns at that point. If it occurs an odd amount of time, then it crosses that point, right? It goes through it. So in this case, our multiplicity of 2 is going to tell us that we're going to touch this point right here. We're not going to cross it. We're just going to touch it and bounce back. All right, and we know that it's going to look something like that. Right, and we'll get to the more specifics as we go through this lesson. Right, but for now, just the rough sketch. Right, we'll get more deep into it later on. All right, so I'm going to start just by finding the necessary information that we need to graph. In this particular problem, we're not going to graph, but let's just find all this information. So to find the end behavior, right, we said that we had needed to know the degree and the leading coefficient, right? We needed two pieces of information. The degree in this case is your highest exponent is going to be 3, and we know that this is an odd number. Our leading coefficient here, we have nothing in front of the x to the third, so it's going to be a 1, right? Our leading coefficient is 1, and this is positive, right? So if you go back and look at that table, we know that a degree of 3, so an odd degree and a positive leading coefficient means our end behavior is going to look something like that. It's going to go down as you go to the left, and it's going to go up as you go to the right. All right? And that's all you need to know here, right? That's all we really want to know. We just want to know where does it go as you go to the left and the right. All right, now let's move on to our zeros. For our zeros, we want to set this function equal to 0, right? So f of x equals 0. That's what we're trying to solve. So let's set this equal to 0. We have x cubed plus 2x squared minus 4x minus 8 equals 0. This one we can factor by grouping, right? So this is another skill that you guys have learned long ago, right? And it makes another appearance here. So this is an application of it. So let's go ahead and try factoring it. We can take out an x squared and we're left with an x plus 2. We can take out a negative 4 and we're left with an x plus 2. So then we're left with an x squared minus 4 and an x plus 2. Right, so this is just factoring by grouping. You may choose to set these equal to 0 and solve, but I'm going to keep factoring, right? It doesn't really matter, right? You guys know how to solve quadratic equations by square rooting, so it wouldn't be super out of the box if you were to just set the x squared minus 4 equal to 0, right? But we can keep factoring. Notice that that's a difference of squares, and I am going to keep factoring just so that you can clearly see what happens after this, right? And notice that when we do this, we get 3 solutions: x equals negative 2, x equals 2, and x equals negative 2. Right, so we get our 3 solutions. And I had mentioned before that the degree can give us some clue as to how many solutions we should get. Right, so if you see a degree of 3, we should expect 3 solutions, and we got 3 solutions. Right, but what happens next is we want to know the multiplicity. Right, so let's go through each solution. X equals negative 2, right? Does that show up more than once? Right? If you check, it does. We have a negative 2 and another negative 2. So x equals negative 2, we're going to say that it has a multiplicity, I'm going to abbreviate it, multiplicity of 2, meaning it shows up twice. All right? And now this x equals 2, for example, it only shows up once, so I'm going to say it has a multiplicity of 1. All right, and that's all the information that we were being asked for, and we can choose to graph it, right? But for now, let's just get used to finding this information, right? We see that it's not incredibly difficult, right? Nothing super new out of the ordinary. All right, so the rest of the examples we're gonna be graphing. To graph, we need some key information. We're going to need to know the end behavior and zeros and multiplicity, which is what we discussed so far. We can also find a y-intercept, right? And finding the y-intercept for a polynomial in standard form is going to be similar to how we did it with a quadratic in standard form. It's just always going to be your constant value, right? So the number without a variable. In any other form, and you're going to see towards the end of this lesson that there's some that are in a factored form. To find the y-intercept, you would have to plug in 0 for x. And some of these shapes of our graphs are things that maybe you haven't seen before, so we don't really know what they're going to look like. And in these cases, we might need some additional points in order to accurately graph, right? So that's just if we really aren't sure what points are going to go where, how it's going to look in between the end behaviors and things like that. We'll get to that as we go through these examples. But sometimes we're going to need some additional points. So we can start with this example. We'll start by finding the end behavior, zeros, and multiplicity, right? So that's something that we've done before in a previous example, right? So I'm going to start with the end behavior, right? And we said with the end behavior that we need to know the degree and we need to know the leading coefficient, right? So the degree here, the highest exponent that we see is going to be 4, right? So that 4 comes from the highest exponent. The leading coefficient is going to come from the number that's in front of this term with the highest exponent, and it's going to be a 1, right? We don't see anything in front of it, so we assume it's a 1, right? And this 4 is even, and this 1 is positive, right? Even positive goes up in both directions, right? So we should expect it to go something like that. So no matter what the rest of our points look like, we know that they both should be going up in both directions. All right, and now for our zeros, we want to set our function equal to 0, right? And our function is x to the 4th minus 5x squared plus 4. Set this equal to 0. I had called these quadratic-like polynomials, meaning you can do whatever you would with a quadratic to these kinds of polynomials, right? And we know it's a quadratic-like polynomial because our middle term has an exponent that is half of the highest exponent, right? So we can set it up in the same way that we would a quadratic. So we're still going to find factors that multiply to the last term and add to the middle, right? So it's going to be minus 4, right? So negative 4 and a negative 1, right? And because our middle term is an x squared, we have to have an x squared inside of our parentheses in our factors, right? And this equals 0. Right, and now let's go ahead and keep factoring, right? These are both difference of perfect squares. So this one's going to be an x plus 2x minus 2. This x squared minus 1 is going to become an x plus 1. Whoa, x plus 1, x minus 1. And now we can set everything equal to 0, so we get negative 2, 2, negative 1, and 1. Right, so setting everything equal to 0, we get these 4 points. I'm going to go ahead and plot those on this graph. Right, so I have a negative 2, and a 2, a negative 1, and a 1. All right. Now for multiplicity, we had said that that is the amount of times that each solution shows up. Right, so negative 2 only shows up once, so does positive 2, and negative 1 and positive 1. They all only show up once in our final answer, right? We only get them as solutions once each time. So all solutions, or all roots, have a multiplicity of 1. Right, and we had said before that odd multiplicity means that we cross that point at the x-axis. All right, so that'll help us when we graph. And now for our y-intercept, right? It's just going to be whatever we get, whatever value of y we get when we plug in 0 for x. And in this case, this is a polynomial in standard form, and we know that the constant is always going to give us our y-intercept, right? So it's just going to be 0, 4. If you didn't recognize that, plug in 0 and you'll get the same thing, right? So hopefully you recognize that pattern. All right, so we're going to have a point right there at positive 4. So we can go ahead and connect some of these points, right? So we know that it's going to go up in both directions, right? And we know that they have to cross at negative 2. We're going to go back up because we need to cross at negative 1. We need to hit the y-axis at 4, but we also need to go back down to hit this 1, and then we need to go back up to hit this 2, right? And we know that it's going to go forever up. Whoa, I kind of messed it up right there. All right, so we know that it has to go forever up in that direction, right? And that satisfies all the criteria that we had just established, right? So it goes up in both directions, it crosses all of our intercepts, our x-intercepts, and it hits the y-axis at 4, right? That's really all we need. So then how do you know that it looks something like this, and let's say it's not, let's say it doesn't go super low, like why doesn't it go like that, for example, and it go back up right there? Truthfully, we don't know that, right? So it could go way down like that, right? And we wouldn't know unless we pick some extra points to graph, right? So I'm going to go ahead and erase that. Yeah, unless we had extra points, we really can't be certain what goes, like, I don't know, in between these two numbers here. If you wanted to know for sure, you would pick a point, right? I would pick maybe between -1 and 2 is going to be -1.5, right? And that's going to be -3/2. So what you really could do is you could plug in -3/2 into our function and see what we get, right? I'm not going to do that here. You guys can verify that on your own. I really am just concerned about you get the correct intercepts and the correct end behaviors, right? But in some other examples, it might be more important for us to be a little bit more accurate with our points, right? We can kind of assume for this one that it's not going to go crazy low like that, right? It's going to still have some sort of shape to it. But again, in some other examples, let's say your intercepts are super spread out and you really have no idea, there's too much space in between them for you to just guess it. Pick some extra points and then see what happens. All right, but for now, this is fine. All right, so let's keep it going with another example. Again, let's just find some key information that we learned in this section. We'll start with our end behaviors. I'm just going to abbreviate it. Right, we want to know our degree, and we want to know our leading coefficient. In this case, our degree is going to be 4, right? Our highest exponent we see is a 4. And our leading coefficient is whatever's in front of that term. It's going to be -2, right? And 4 is even. I almost wrote odd, right? But this is even. And our leading coefficient is negative, right? Even negative goes down in both directions. Right, so we don't know anything that goes in between yet, right? So anytime that we talk about our end behavior, right, really we don't know what goes on in between, right? We don't know what goes on. It might go up and down like that, but we know for sure that it's going to go forever in some direction, right? In this case, it's going down in both, right? So that's just what we mean with our end behavior, right? Let me go ahead and erase that, right? But we know for sure it's going down. And as far as our zeros go, as always with our zeros, you want to set your entire function equal to 0. So -2x to the 4th plus 2x squared, right? Set it equal to 0. And you want to take out a common factor, right? So we only have 2 terms here. Our options are limited, right? But we can just try taking out a common factor. They do share a factor of -2x squared, right? So the greatest factor that they have in common. And this is going to leave us with an x squared minus 1, and this equals 0. All right, and we can keep factoring, right? So -2x squared can hang out out front, and x squared minus 1 is a difference of squares. So it becomes an x plus 1 and an x minus 1. Right, so now we have -2x squared equals 0, x plus 1 equals 0, and an x minus 1 equals 0. Right, so we have over here, we can divide both sides by -2, and we get x squared equals 0. Right, if we go ahead and square root both sides, we get x equals 0, but this actually shows up twice. Right, even though we have one answer, we wrote it down once, right, it was an x squared. Right, so this just means x times x, and if you want to set each of these factors equal to 0, right, you can clearly see that there's 2 of them, right? And for x plus 1 equals 0, we just get one of those, and for x minus 1 equals 0, we get one of those, right? But our only one that shows up twice is going to be this x equals 0. So when we go to answer our question on multiplicity, right, x equals 0, right, has a multiplicity of 2, right, because it shows up twice. Now x equals -1 and 1, they both have a multiplicity of 1, right? They only show up once. Right, so something else that might be useful for us is the y-intercept. Now this is a polynomial in standard form, right? So it's not factored at all, right? It's completely in standard form. We can assume that there's an imaginary 0 here, right? So plus 0, right? That's going to be our constant in this case. So this just means our y-intercept is going to be at 0, 0. Right? Maybe you didn't recognize that, right? So maybe this looks a little different than something that you've done before. You would just plug in 0, right? So we would get -2 times 0 to the 4th power plus 2 times 0 squared. And 0 to the 4th power is 0. So we get -2 times 0 plus 2 times 0 to the 2nd power is 0. So we just get 0 plus 0, which is 0. Right, so I'm going to go ahead and plot the points that we found so far. We have an x-intercept of 0, -1, and 1. All right, and we have a y-intercept also at 0, 0. Right, that doesn't really give us much information. So maybe we can find another point, right? So I'm going to pick a point maybe like right here. I'm going to say 1/2. So any additional points we can solve down here. I'm just going to pick for x equals 1/2. Right, so I'm going to do f of 1/2 is just going to be -2 times 1/2 to the 4th power plus 2 times 1/2 to the 2nd power. And this is going to get us -2 times 1/16. Right, how did I get that number? I just raised the top and the bottom to the 4th power. 1 to the 4th is 1, 2 to the 4th is 16. And I'm going to do the same thing with that 1/2 squared. So we get plus 2 times 1/4. Right, square the top and square the bottom. And then we get -2/16. That's going to cancel out, and we're going to get -1/8. And then this is also going to cancel out, and it's going to become 1/2. All right, so we can find a common denominator. Or my bad, let me just, yeah, okay. That was fine. It becomes -1/8 plus 4/8, and we get -3/8. Right, so we know that at -1/2, it's going to go down -3/8, and it's going to be somewhere in the middle right there. Right, that should be enough points to graph. Right, we know that it's going to go forever down in both directions. Right, so down and down. Oh, I made a mistake. Right, it's positive 3/8. Oh, my bad. All right, positive 3/8 is gonna go up here, up. So it's gonna go up there. Whoa, I'm doing something completely wrong. I keep making mistakes. Okay, it's gonna look something like that. Let's start crossing. We know it's gonna cross at -1, right? Because it has a multiplicity of 1. It's gonna touch and bounce at 0, and it's gonna cross at 1. Right, so that touch and bounce, it's not going to cross, right? It's going to look something like that. But we know it also crosses at 1, right? So our graph is going to look something like that. And if we want to be a little bit more accurate, we would pick additional points. But this should be enough, right? We just want to know what the general shape of it looks like. All right, so let's try another one. As always, let's start with our end behavior. All right, end behavior. Is going to be our degree and our leading coefficient, right? Our degree is 3, right? That's our highest exponent. And our leading coefficient is 1, right? So the number in front of the x cubed is 1, right? This 1 is positive, and this 3 is odd, right? Odd positive, we can expect it to go down, going to the left, and go up as we go to the right. All right, now let's find our zeros. All right, we want to set our function equal to 0. So x cubed minus 12x squared plus 36x equals 0. Here we can take out a GCF. In this case, it's going to be x. Right, so we can take out an x and we're going to be left with an x squared minus 12x plus 36 equals 0. All right, and now on the inside, we want factors that multiply to 36 and add to negative 12. So we get x times x minus 6 and x minus 6, right? Negative 6 and negative 6 multiply to 36 and add to 12. And now we get x equals 0, x equals 6, and x equals 6. And as for multiplicity, right, this 0 has a multiplicity of 1, and this x equals 6 has a multiplicity of 2, right, because they show up twice, right? Really, it only counts once, but it shows up twice. All right, so I'm going to go ahead and plot these on the graph, right? So I know that there's a 0 right here, and there's a 6 right here. All right, and now for our y-intercept, right, similar to the last problem, our y-intercept in this case is going to be 0, right, because we don't have a constant, right, and it's in standard form. So it's going to be 0, 0. It's going to be at the same spot right here, right? So this is an example of something where maybe I'd want to add a couple more points, right, just because really there's so much space between that 0 and that 6 that anything could happen there. We don't really know what's going to happen. So I'm going to I'll start with maybe 1, right? So I'll start with an x equals 1, right? So an f of 1 is going to give us a 1 cubed minus 12 times 1 squared plus 36 times 1, right? And so we get 1 minus 12 plus 36, right? 1 minus 12 is going to get us negative 11. And negative 11 plus 36 is going to get us 25, right? So for x equals 1, we get y is 25, right? That's going to be way off the graph, right? So I'm going to go maybe by tens, right? So 10, 20, 30, 40, and so on. So it's going to be somewhere right there, right? 25. And then right, so I imagine as we go higher, we're going to get a really big number, right? So I imagine maybe we can pick like 5, for example, x equals 5. Right, so we get 5 cubed minus 12 times 5 squared plus 36 times 5, right? So these are going to get us really big numbers. We get 125 over here minus 12 times 25 is going to get us 300, right? You can do it off to the side if you need. And then 36 times 5 should get us 180. Right, so we get 125 minus 300 is going to get us negative 175, and negative 175 plus 180 should get us 5. Right, so at x equals 5, we get y is 5. Right, so we get something right there. Right, so that kind of helps us a little bit to graph our points. So we know that the end behavior, it's going to go down as you go to the left and up as you go to the right. So we can expect it to go down like that. We know that at 0, we have a multiplicity of 1. Right, so it's going to go down like that. So we're going to cross it and touch this point right here. Right? I don't know what happens later on in the graph. It might keep going up, right? But I'm just going to go back down to hit that point right there. And it's going to touch and bounce back at 6, and then it's going to go forever up, right? Because we know because of our end behavior, it's going to go up as you go to the right. And we know because of our multiplicity of 2 that it's going to touch 6, right? And not cross it, right? So we can expect our graph to look something like that. All right, so now something like this one you do need to be a little bit careful with, right? Because notice that it is not in standard form, meaning our term with the highest exponent does not come first, right? Notice our highest exponent here is 4. So when we go to determine our end behavior, right, our degree, we're not just going to look at the first number that we see. So it's not going to be 3. It's going to be the highest one. In this case, it's going to be 4. So our degree is going to be 4. And our leading coefficient is going to be whatever's in front of that x to the 4th, and it's going to be a positive 3. Right, so 4 is even, and 3, well, let me draw that a little bit better. And 3 is positive. Right, even positive, we go up in both directions. Right, now to find our zeros, right, set this equal to 0 and factor it. So you get negative 4x to the 3rd, right, plus 3x to the 4th equals 0, right? Take out a GCF. In this case, it's going to be x to the 3rd. So we get x to the 3rd, negative 4 plus 3x equals 0. And let's just set each of these equal to 0. So we get x to the 3rd equals 0, and negative 4 plus 3x equals 0. So here we get x equals 4/3. Right, we just add 4 on both sides and then divide by 3. And here we get x equals 0, but we get x equals 0 3 times, right, because of that exponent of 3, right? If you cube root this, then the cube root of 0 is just 0, right? But we get it 3 times. So this x equals 0 is going to have a multiplicity of 3, right? But this x equals 4/3 is going to have a multiplicity of 1, right? Meaning both of these points are actually going to cross where on the x-axis it's going to be 0 and 4/3. So at 0 and at 4/3, which is going to be a little bit more than 1, so somewhere right there, we're going to cross those points. Right, and we know that it's crossing because of the odd multiplicity. All right, and so again, similar to all the other examples, there is no constant here. Well, not all the other examples, but the ones that we've done recently, there's been no constant term, meaning that our y-intercept is going to touch at the point 0, 0. Right, so now to find where the rest of it goes, right, so we don't need a crazy amount of points. I'm maybe just going to pick 1 and 2. Right, so I'm going to pick x equals 1 and x equals 2. Right, it doesn't really matter. So I'm going to do f of 1 is going to get us negative 4 times 1 cubed plus 3 times 1 to the 4th. And it's going to be negative 4 plus 3, and that's going to get us negative 1. All right, so when x equals 1, y is negative 1. So we get a point right there. All right, so now when x equals 2, right, f of 2 is going to get us negative 4 times 2 cubed plus 3 times 2 to the 4th power. And that's going to get us negative 4 times 8 plus 3 times 16. And negative 4 times 8 is going to get us a negative 32. And 3 times 16 is going to get us 48. So this is going to get us 16. All right, so we can go ahead and plot this point. 216 is going to be way up there. All right, so somewhere all the way up there. All right, but that's actually helpful for us, right? Because that helps us determine what the rest of this graph looks like. So we know that the end behavior is meaning it's going to go up in both directions, right? We know that at this point it has to go up, right? So I'm going to bring it back down. We know that it has to cross both of these points. So it's going to cross at 4/3. It has to hit this point right here, and it might go a little bit down, right? But we don't know exactly. But we don't, right? We don't have to be super precise, right? As long as our points are drawn to some accuracy, right? And we're gonna draw a cross right here. We're gonna cross this 0, 0, and it's gonna go up like that, right? So now if you were to properly graph this, if you zoom in really close on the 0, there's gonna be a little bit of a bump there, right? And you can verify this. I'll see if I can include it in this video, but I know I went over it in class. If you go to Desmos, right, it's an online graphing calculator. It's built into the SAT software, so when you go to take that, it'll be helpful. But if you put this into Desmos and you zoom in really close on that point where x equals 0, then you're going to see that there's a little bit of a bump there, right? But we know regardless, it is going to cross. It is going to cross it, but the multiplicity of 3 is going to give it a little bit of a bump. And the multiplicity of 1 is just going to cross like normal. All right? And that's it for that one. All right, let's keep it going. Let's find the end behaviors of this one, right? So as always, we need the degree and leading coefficient, right? The degree here is going to be the highest exponent. In this case, it's 3. And our leading coefficient is going to be the coefficient in front of that, x cubed, and it's going to be a 2. This degree is odd, and this leading coefficient is positive. Odd positive is going to go down to the left and up to the right. All right, now let's find our zeros. All right, set this equal to 0, 2x cubed minus 6x squared. Right, take out a GCF. Here we can take out a 2x squared. And we're left with an x minus 3. And then so we get x equals 3. And here we get x equals 0, right, because you can set 2x squared equal to 0. Right, divide by 2. And then you get x squared equals 0. Now this just means x equals 0, but twice. Right, so this, in terms of multiplicity, this is going to be twice. Right, so this is a multiplicity of 2. And x equals 3 shows up only once, so this is going to have a multiplicity of 1. All right, so I'm going to plot those points on the graph. 0 is going to be right there, and 3 is going to be right there. All right, as always, well, not as always, but just like the previous examples, we don't have a constant term here, so this y-intercept is going to be at 0, 0. Right, so at the same point right there. That doesn't really give us that much information. So let's find additional points. All right, so I'm going to pick 1, for instance. Right, that should be fine. F of 1 is going to get us 2 times 1 cubed minus 6 times 1 squared. And then we get 2 times 1 minus 6 times 1. And that's going to be 2 minus 6, which is negative 4. So that means when x equals 1, y equals negative 4, I'm going to go way down there. Right, and that should be fine for our graph. Right, we know that the multiplicity of 2, it's going to touch and bounce. Right, so that means from this point, if we're going to go up, it's going to touch it and bounce. So that means I need to go back down this way. Right, forever going down. Right. And then from this point, right, I might go down more, right? I don't know exactly, right? If I want to pick another point to be sure, you can, right? But, right, that's fine. As long as you have another point, that's fine. And we know that the odd multiplicity of 3 is going to go cross, right? So it's going to cross it. It's going to look something like that. Let me go ahead and erase this. I'm going to drag it all the way down, right? So it's going to look something like that. All right, so now this looks a lot different than the problems that we've done before, right? That's because this is something that's already factored for you, right? So if you want to write it with all the factors, right, another way that you can write it, this is f of x is, this negative on the outside is a negative 1. X minus 3 to the second power, squaring anything just means that you're multiplying it by itself twice. So you get x minus 3 and x minus 3. We have an x plus 1. And we actually have another x plus 1 that's squared, right? And again, squared means you're going to multiply it by itself twice. So you get an x plus 1 and another x plus 1, right? So this is it fully factored out, fully expanded, right? And so that's going to help us to find our intercepts, right? But to find our end behaviors, right, our end behavior, we need to know the degree, right? But we don't know the degree immediately by looking at it when it's written like this, right? But notice that if you were to FOIL this out, if you were to FOIL your binomials and then distribute each term and just you're going to fully expand it, which, I mean, that's going to be a hassle, right? So you don't want to do that. But if you were to do this, you would multiply an x to the first, and 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 an x to the first, right? 5 of them, right? There's 5 x to the first powers that you're going to multiply with each other, right? So that means your highest exponent is going to be 5, right? And this is an odd number. Your leading coefficient is going to be whatever's in front of your entire factored form, right? In this case, it's going to be a -1, all right? -1, and this is going to be negative. Odd negative is going to go up as you go to the right, to the left, and it's going to go down as you go to the right. All right, and now let's find our zeros. To find our zeros, we're going to set this function equal to 0. So -1 times x minus 3 times x minus 3 times x plus 1, x plus 1, x plus 1. Set this equal to 0. Right, so set all of these factors equal to 0, and we should get x equals 3, x equals 3, x equals -1, x equals -1, and x equals -1. Right, and this -1 on the outside, it's a coefficient. If you divide the entire thing by -1, right, so we can divide both sides by -1, we still get that it equals 0, so it goes away when you try to solve, right? Now in terms of multiplicity, right, x equals 3, notice that it shows up twice, right? So it has a multiplicity of 2. Now x equals -1 shows up 1, 2, 3 times, right? So it has a multiplicity of 3. All right, so I'm going to go ahead and plot those points. All right, so I have a 3 right here, and a -1 here. Right, another important point for us to find is our y-intercept. Right, so now in this case, our y-intercept, it's not going to be as obvious as the others. Right, here we actually want to plug in a 0. Right, so we get -1 times 0 plus 3 times 0 plus 3 times 0. No, it's not plus, it's minus. 0 minus 3 minus 3, 0 plus 1, 0 plus 1, and a 0 plus 1. Right, so we get -1 times -3 times -3, and then we just get a bunch of 1s. Right, and then 1 times 1 times 1, that's just 1. And -3 times -3 is 9, and 9 times -1 is going to get us a -9. Right, so our y-intercept is going to be all the way down here at -9. Right, it's going to go off our graph a little bit. All right, and we can maybe pick another point, right, just to see exactly where it goes. As always, we can pick 1. Right, so I'm going to pick f of 1. And that's going to get us -1 times 1 minus 3, 1 minus 3, 1 plus 1, 1 plus 1, and 1 plus 1. Right, you can plug it into the original if you're okay using the exponents, right? It's not going to be any harder. Right, so we can do -1 times -2 times -2 times 2 times 2 times 2. Right, and 2 times 2 times 2 times 2 times 2, 5 times is going to get us 32. And now 32 we got from doing a negative times a negative, so it's positive, times -1 is going to get us -32. Right, so we know that we're going to go way down there if we do a -32, right? So just to roughly sketch our graph, we know that we're going to cross at -1, right? So we're going to go up in that direction. We're going to cross because it has an odd multiplicity, and then we said that this is going to give it a little bit of a bounce, right? So a little bit of a curve there, and then you're going to go down. You're going to hit your y-intercept, and as you keep going down, you're going to go way down, right? We're not going to be able to picture that here, but we're going to go way down there, and so now our multiplicity of 2 means we're going to touch this point at 3, and we're going to go back down. Right, so we can expect it to look something like that. Right, it might not be the most precise graph, but it's accurate enough to where we have where we're using the information that we found. Right, and again, if you want to be absolutely certain of what your graph looks like, refer to Desmos. Right, try to mess around with Desmos and see what this gets you if you type it in. Right, you should see something with at least a little bit of a similar shape. I imagine it'll be a lot longer, but you should expect to see something a little bit similar. All right, so one last example. Again, same information as always. Let's start with our end behavior. Right, and again, if it's written in this way, right, so this is similar to the one that we just did. This is the same as writing f of x is -1. Right, the exponent of 2 means x plus 2 times x plus 2. This exponent of 2 means x minus 3, x minus 3. Right, so what does this mean? Well, if you were to FOIL this out, which you shouldn't do, right, that's going to give you something that's not really going to help you. We get x to the first times x to the first times x to the first times x to the first, right? So we get 4 x's, and it's going to be a degree of 4. Degree of 4, right? And this is even. And our leading coefficient, this one also has a negative out front, right? So our leading coefficient is going to be negative. Even negative goes down, right? They go in the same direction and they both go down. Right, so let's find our zeros now. Our zeros, we're going to set this entire function equal to 0. I'm going to do the factored form because that's going to make it easier to see our multiplicity. Right, I think in class I took a square root, but that only gave us one answer, which we will get one answer, but it appears twice in our problem, in our graph. Right, so we're going to set all of these equal to 0, so we should get x equals -2, x equals -2, x equals 3, and x equals 3. All right, so I'm going to go ahead and plot those points. We have a -2 right here, and we have a 3 right here. All right, and our multiplicity now, right, x equals -2 has a multiplicity of 2, right, and so does x equals 3, right, so both of these have a multiplicity of 2. You can see that they show up twice, both of them. All right, and for any additional points, right, so let's say a y-intercept, right, let's plug in x equals 0, right, so f of 0 is going to get us -1, 0 plus 2 squared times 0 minus 3 squared. All right, so now I'm plugging into the original, not the factored form. All right, we're going to get -1 times 2 squared times -3 squared, and that's going to get us -1 times 4 times 9. 4 times 9 is 36, times -1 is going to get us a -36. All right, so it's going to go way down there, right? And I can even, if I want to fit it on the graph, I can change the scale of it, right? -12, -18, -24, and so on. And -36 is going to be somewhere down there, right? So we know that this is going to be a really long graph, right? So it's not going to fit on this graph that we see here. But we can still use the information that we found to kind of do a rough sketch of it. So we know that both of our solutions, right, that we see in red, touch the graph at the x-axis, and it's going to bounce, right, because they have a multiplicity of 2. So it's going to touch and bounce, right? It's going to touch and bounce, right? And we know that it has to cross the y-intercept. I imagine it's going to go way down there, but eventually it's going to have to come back up to hit this point right here. And then we know because of our end behaviors that we're going to have to go down in both directions, right? So this is a rough sketch of our graph. All right, so in sum, we learned some more information about polynomials, right, and behavior, zeros, multiplicity, and that's all to help us graph, right? And now we can pick some additional points if we need, but really we just need to know what the overall shape of it looks like, and as long as you can graph them to some accuracy, then you'll be fine. But if you really want to be sure that you're graphing it accurately, plug it into Desmos, right? And I encourage it for the homework, right? Just to check your answer and see that you're actually graphing it correctly, right? So it doesn't hurt to use that to as some reference, right? But really the math that we're learning here isn't really anything new, right? Because I've taught you guys before how to solve for the solutions here in a problem like this, or in polynomials in general, right? We had a whole section on just solving polynomials. So that part of it shouldn't be new, right? Just knowing what to do with those answers is a little bit new and maybe it takes some getting used to.